Every day, thousands of tons of shrimp shells end up as waste. Most people never think twice about them, but hidden inside these discarded shells is a natural material that could help replace the plastic polluting our planet. Today, we're taking you inside the factory where shrimp shell waste is transformed into biodegradable bioplastic, step by step from start to finish. It begins far from any laboratory, at seafood processing plants where workers peel and devein thousands of shrimp every hour. The meat goes to market. The shells, heads, tails, exoskeletons used to go straight into landfill, adding to a global mountain of seafood waste that most people never think twice about. Now they're loaded into refrigerated trucks and shipped to a specialized facility built for exactly one purpose: turning that waste into raw material. Inside the receiving bay, shells are dumped onto a steel platform and moved into cold storage because bacteria grow fast on organic waste, and a single delay could spoil an entire batch before processing even starts. Every incoming load is logged and weighed, so the plant always knows exactly how much raw material it has moving through the system at any given moment. From storage, the shells move onto a vibrating conveyor for sorting. Automatic optical sensors scan the stream, flagging stray fish scraps, plastic fragments, or oversized debris. Workers in white suits stand along the line doing manual inspection, pulling out anything the machines miss. This step matters more than it looks. Any contamination here carries through every later stage, and a batch of shells with the wrong material mixed in can throw off the entire chemical process down the line. Next comes industrial washing. The sorted shells drop into massive rotating drum washers, tumbling under high-pressure water jets that blast away sand, salt, and leftover tissue. The drums rotate continuously, and the water itself is filtered and recycled back into the system, because a factory processing tons of shells daily can't afford to waste that much fresh water. What comes out the other end looks nothing like what went in. Clean, pale shell fragments instead of the pink, salty debris that arrived that morning. Even a small amount of leftover salt can interfere with the chemical reactions waiting later in the process. So this washing stage often repeats in multiple passes before the material is cleared to move on. But the real transformation hasn't even started. The washed shells feed into industrial crushers, then into hammer mills that pound them down into a coarse, uniform powder. The finer and more consistent the particle size, the faster and more evenly the chemicals in later stages can penetrate the material. So operators monitor the mill output closely, screening out any fragments that are too large. Conveyor systems carry the crushed material toward a bank of continuous drying tunnels, where controlled heat strips out every trace of moisture. Temperature has to stay within a narrow range. Too hot, and the material degrades before processing even begins. Too cool, and residual moisture ruins the chemistry in the next stage. This is the point where shrimp shells stop looking like shrimp shells at all. They're now a dry, chalky powder, ready for the process that actually unlocks what's inside. This next machine completely changes the material. The powder enters sealed chemical tanks for demineralization, where a controlled acid solution dissolves away the calcium carbonate that gave the shell its hardness. Reaction control systems monitor temperature and concentration constantly, because this stage is genuinely dangerous if mismanaged. Too aggressive, and the material breaks down. Too weak, and minerals remain trapped inside, contaminating everything that follows. Safety systems continuously vent and monitor the tanks throughout. What's left after demineralization moves straight into deproteinization, another set of reaction vessels where an alkaline solution strips away the proteins bound to the shell structure. This is the step that finally isolates the substance the entire factory exists to produce: chitin, a natural polymer found in crustacean shells, insect exoskeletons, and fungal cell walls. Without this stage, the leftover protein would trap moisture and weaken the final material, so the reaction is allowed to run its full cycle, no matter how tempting it is to speed up the line. One tiny mistake here could ruin the entire production batch, so operators track pH and temperature on every tank in real time. The isolated chitin then goes through multiple purification stages, repeated washing, neutralization, and filtration through industrial centrifuges that spin the material at high speed to separate solids from liquid. Quality monitoring stations sample the output constantly, checking purity before it's cleared to move forward. Nothing advances to the next stage without passing this checkpoint. This single process determines whether the bioplastic succeeds or fails. The purified chitin enters a series of controlled reaction vessels where a precise chemical treatment converts it into chitosan, a more flexible, more soluble form of the same natural polymer, and the actual building block of the bioplastic. Mixing systems keep the reaction uniform throughout the vessel, while process control computers track every variable, because chitosan's properties, its strength, its flexibility, its final texture, are all decided in this one stage. From here, the chitosan moves into industrial mixers where it's combined with natural plasticizers to create the actual bioplastic solution. Viscosity control is critical. Too thick, and the material won't flow evenly through the next machines. Too thin, and the finished product comes out weak and brittle. Lab technicians pull samples continuously, adjusting the formulation in real time until the solution meets exact specification. This is also where the final character of the product is decided. A slightly different plasticizer ratio can mean the difference between a rigid packaging film and a flexible, stretchable sheet. Once approved, the solution is pumped toward the forming stage. Depending on the target product, it either goes through extrusion machines that push it into continuous sheets, film casting equipment that spreads it into thin, uniform layers, or systems that pelletize it into feedstock for injection molding elsewhere. Every one of these machines runs under tight speed and pressure control, because uneven flow at this stage shows up later as weak spots in the finished sheet. Watching raw shrimp shell powder emerge here as a smooth, continuous sheet of material is where the transformation finally becomes visible to the naked eye. The freshly formed material passes through long cooling tunnels, guided by a series of rollers that keep tension even across the sheet. Controlled cooling locks the molecular structure in place. Cool it too fast, and the sheet warps or cracks. Too slow, and the line backs up behind it. From there, automatic cutting machines slice the material to exact dimensions, while laser inspection systems scan every pass for micro defects invisible to a human eye. Then comes the stage that decides whether any of this reaches the real world. In the quality control lab, technicians run the material through thickness measurement, tensile strength testing, and flexibility trials that bend and flex samples until they know exactly how the material will hold up in use. Water resistance testing checks how the bioplastic behaves under moisture. Essential, since one of its biggest advantages over ordinary plastic is that it breaks down safely instead of persisting for centuries. Biodegradability testing confirms exactly that, tracking how quickly samples decompose under controlled conditions compared to ordinary petroleum-based plastic, which can persist in the environment for centuries. Microscope inspection and computer-controlled analysis catch anything the naked eye can't, scanning for microscopic voids or inconsistencies in the material's structure, and any batch that fails even one test gets rejected before it ever reaches packaging. The material that passes moves to the final stage, automatic packaging lines that seal, label, and stack the finished bioplastic sheets and pellets. Robotic palletizers stack the packaged product for the warehouse, where it waits for shipping to manufacturers who'll turn it into everything from food containers to medical packaging, agricultural film, and even wound dressings, since chitosan-based material is naturally compatible with the human body. What started as a pile of discarded shrimp shells, the kind thrown away by the ton at seafood plants around the world, leaves this factory as something entirely different. A biodegradable material capable of replacing the plastic that's been piling up in oceans and landfills for decades. It's proof that some of the most sustainable materials on Earth aren't invented in a lab from scratch. They're rediscovered in the waste we've been throwing away all along.